Okay, so today we're talking about hyperbolas. And if you recall what a conic section is, it is this set of all points that satisfy a certain criteria. Look back through your notes and remind yourself about what those criteria were for conic sections like circles, ellipses, and parabolas. A hyperbola is a set of all points in a plane where the difference of the distances from two fixed points, the foci, is a positive constant. And that sounds really complicated when I say it out loud like that, but let's break it down. It's really not that bad. So if I were to look at this first figure here, here's a hyperbola, which you'll see there are two unique branches. Again, a branch is just a fancy way of saying the curve. And if I were to choose an arbitrary point on a branch, let's say, for example, this point here, and I were to find the distance from that point to the first focus, which is always inside the branch, and we'll call this one D2, and find the distance from that point to the other focus, which is inside this branch, which we'll call D1, we'll see that D2 minus D1 gives us some positive constant. Well, if I were to choose any other point on this hyperbola, so let's say I chose that point there, and I found this distance, which is going to be a different D2, and this distance here, which is clearly a different D1, but D2 minus D1 is going to be the same positive constant. So no matter where we are, so even if I choose this point here, a larger D2 and a much larger D1, D1, D2 minus D1 is always going to remain the same positive constant. That's what makes it a hyperbola. So don't stress out too much about what this definition gives us here, but just know that's how we define what a hyperbola is. Now let's look at some specific characteristics of a hyperbola. Now let's look at this figure here because I think it'll help us out. So here, you will notice that on each branch we have a vertex. So we have two vertices, and like we just mentioned, inside each branch we have two foci. So each one of these are going to represent a focus. And exactly halfway in between our two vertices and halfway in between our two foci, we have our center here. Well, just like we did with ellipses, there are some key values that we can actually start finding. The distance between our center and our vertex is going to be our A value. And as you can probably figure out, we'll be using these in our standard form equations. And the distance between our center and our focus, this is going to be our C value. Now, the book uses C, but you know me by now. I like to actually use lowercase f because it doesn't confuse it with where the center is. But our F value is going to be the distance between our center and our focus. And you're probably asking yourself, well, what about B? Is there a B value? And there is, and we'll get to that in just a second. Now let's look at the standard form equations of a hyperbola. So let's look at this part right over here. So if you're looking at these equations, the first thought you probably have is that it looks a lot like ellipses, and you would be absolutely right. The equations are incredibly similar. There's just one small difference. Can you spot it? Right. We are subtracting these terms instead of adding them. Other than that, they look completely the same. But that is a huge difference. The fact that we are subtracting these terms gives us insight as to whether or not which term is positive actually makes all the difference in terms of what our hyperbola is going to look like. Specifically, if our x term is positive, we will see that our transverse axis, which again is the axis that runs through the center and our vertices and our foci, that's going to be horizontal. Think x as being horizontal. So if our x term is positive, our transverse axis is horizontal. In the second diagram, our y term is positive, therefore our transverse axis is going to be vertical, which means our branches are going to be opening up and down. So let's actually write that. So the fact that our positive term, which term is positive, it determines the direction of our opening. Okay, so it's going to tell us whether or not our transverse axis is horizontal or vertical, thereby telling us which way our transverse axis is going to open and then which way our branches are going to open. Okay, We'll get back to our standard form equations, but I do want to break down something real quick because in order for us to really understand what these A and B values give us, we need to go back to looking at each diagram. So let's look at them real quick. Again, our A value gives us our distance between our center and our vertex, which isn't labeled here, but I'll just quickly label that. So the distance from our center to our vertex, this is our A value. And the distance from our center to our focus, which isn't written here, but this is our F value. Okay. Now this part's going to seem a little strange, but bear with me. If I were to take that same length of F and draw it from our center A, so to do something pretty much like this, and align it so that it's directly above our vertex, I would then be able to draw this length here, and I can label this as being our B value. And that B value is exactly what you might think or suspect that it is. I could draw that same B value right over here. So I can go ahead and do that, B, and draw it down, up and down both ways. And this entire B line that I have here, this is our conjugate axis. And I'll just write that here. Our conjugate axis. There's our conjugate axis. Now, why do I care about our conjugate axis? Well, one, I need it so that I can write my B value up here in my standard form equation. But more specifically, I'm going to use both my A and my B values to draw my intersecting asymptotes. I'm going to be using these asymptotes actually to draw these branches. So what do these asymptotes look like? Well, I'm going to use my A and B values as I mentioned before. So in this case, I'm going to be going from the center. I'm going to start from the center. I'm going to go up B units and to the right A units until I get something that looks like this. So I'm going to go up B over A, and I'm going to draw my asymptotes that look something like this. In other words, I'm using my B over A to be the slope of this asymptote, because if you look at that asymptote, it's just a line. It's just a diagonal line, which we can write the equation for any line as just simply using a point and its slope, which in this case is B over A. So I could also draw the asymptote to help draw the other part of the branch. So in this case, I'm going to go up B, back A, and that would give me another asymptote that goes like this. And once you have your asymptotes, all you really need is your vertex, and you can just sketch your branches hugging those asymptotes. I don't require us to find any additional points. Really, we just need our center, our vertices, and our B and our A values. So whenever I'm drawing my asymptotes, I use my B and my A values to help guide the slopes of my asymptotes. And let's take a quick look at what that equation would look like. So since these are lines, I'm going to write these in point slope form. So we would write the following: y minus our k value, and we're just choosing a point on our asymptote. Probably make the most sense to use our center. So y minus k, which is the y value of our center, hk, is equal to b over a times x minus h, which is just the horizontal component of our center. That gives us the first asymptote equation. What about the second one? Well, it's just the slope, but opposite. So here, I can just write that succinctly as plus or minus b over a. Just to really hammer this home, let's look at hyperbola where our transverse axis is horizontal. Let's look at the second diagram right over here. When our transverse axis is vertical, pause the video right now and just ask yourself, what would my A, B, and F look like in this particular hyperbola? Well, our A value, again, is the distance from our center to my vertex. So I'm going to say this is my A. My F value is the distance from my center all the way to my focus here, which is going to be F. And my B value, which I'm not going to redraw my F right over here, but my B value would go out perpendicular to my transverse axis. So we draw something like here, B. And my asymptote would be the line that starts at the center and goes up A over B. So up A, and let me just keep it here, over B. So after a while, it starts to almost kind of look like, that's actually a terrible asymptote. Probably tells me that I should be extending this out a little bit more. So this would start to look something like this. And I can go ahead and extend this in all directions. Up A, back B to draw my other one. And what would the equations for those asymptotes look like? Again, using my center as my point, we would say y minus k is equal to plus or minus, and because now my transverse axis is vertical, I can then say my slope is going to be a over b plus or minus x minus h. So really, once you have your asymptotes, the hyperbola is fairly simple to draw because that assumes that we know our a and b values, which we can get from knowing where our center and our vertices and our foci are. Going back to the standard form equations for these hyperbolas, should be pretty easy to remember because they're very similar to ellipses. Just remember that we're subtracting them, that the term that is positive will determine the transverse axis orientation. So if the x is positive, then it's horizontal. Y is positive, then our transverse axis is vertical. Our a squared and b squared have nothing to do with which one is a larger value. Always remember that a squared is under the positive term. I'm going to go ahead and write that down. Our a squared is always underneath our positive term. And that makes sense if you think about it. Now, just to recap a couple of quick definitions, and you could pause the video and write these on your own if you'd like, but I'll just jot them down here. Our a value is the distance from our center to each vertex. I'm going to jump to the f real quick. Our f value is the distance from our center to each focus. And our b value is the distance from our center to each endpoint of the conjugate axis. And if you recall what our a, b, and f values do, so just looking back here, we've got our a, we have our b, and we have our f. We've got a right triangle, which means the relationship between all of them is simply the Pythagorean theorem. A squared plus b squared is equal to f squared. And review what that relationship for A, B, and F are, what that is for ellipses, because it's going to be pretty similar. And while you're at it, might as well also look at the eccentricity, if you recall. Remember, eccentricity describes how flattened out, or how ovally, if you will, an ellipse gets. Turns out we can also describe the eccentricity of a hyperbola, and it's also going to be defined as being our F over A value. And all that means is our hyperbola is just really kind of just flattened out after a while. It's going to look something like this. So the larger the eccentricity, the more flattened out, if you will, our hyperbola gets.